And at the end of lecture on Wednesday, we talked about the multi-step process that takes place when you put zinc hydroxide in solution and then add ammonia. So are you guys going to talk the whole class period today? Okay, thank you. So we talked about going through and thinking about what could happen with a complex ion formation. Now, the first question everyone asks is, how do I know that zinc forms that complex ion? What do we, how can I tell? Like, I don't know enough about the transition metal chemistry yet to even know if a complex ion is going to form. And the thing that is going to give us the evidence that a complex ion will form is going to be your KF table, which is your formation constant. Just like we look at particular salts, like, you have sodium chloride. There's no KF value for that. The reason for that is because it's completely soluble. So any salt that has a KSP value, we know it's going to be insoluble, at least according to our Chemistry 121 definition. Same thing happens for complex ion formation. If you see a complex ion on the KF table, we know that a complex ion is going to form. So when I tell you you have zinc 2+ in solution and you put ammonia as a reagent in there, then you're going to know that a complex ion is going to form. And the only way you can tell is if you look at the KF table. And if you don't look at that table, you're never going to get this problem right. So on the KF table is this complex ion that forms. So we know that zinc is going to form a complex ion when ammonia is interacted with that. So make sure you're familiar with the table that is given in the lab manual. And when you're taking an exam, like I said, you want to look at that first. So we went through and we showed that there was evidence that a complex ion would form. And then the next question is, how can we approximate the concentration or the solubility when we add a zinc solution and ammonia together? So the question we're going to start with is, what is the solubility of zinc hydroxide in 15 molar NH3? So we don't have an aqueous solution anymore. The solution is completely different. This is going to tell us, and if we look at our KF table, that a complex ion could form. We showed that overall reaction at the end of lecture on Wednesday, and it's written here. Remember, this is a two-step process. The first thing that happens is the zinc hydroxide forms an equilibrium with zinc 2+ ions and OH- ions. The zinc 2+ ions are then going to interact with the ammonia to form this complex ion. So how can we look at the various steps of this, and how can we set up a problem to solve? Again, we're going to use an ice table. The zinc hydroxide is a solid, does not show up in our ice table. The ammonia, we have an initial concentration of 15. And before we add any of the ammonia, or initially, we're going to have a concentration of 0 for the complex ion and 0 for the OH-. When we allow this reaction or this equilibrium to be established, the change in concentration is going to be plus X for the complex ion, plus 2X for the OH- ion, and minus 4X for the ammonia. This gives an equilibrium concentration of 15 minus 4X for our ammonia, X for the hydroxide, and 2X, X for the complex ion and 2X for the hydroxide. From the previous notes on Wednesday, our K expression is equal to the KSP times the KF, because that's the two steps that are occurring. If we multiply those two together, we get 1.3 times 10 to the minus 7. So this is going to be our K for this overall reaction. the K expression that we can set up will be the equilibrium concentration of the Zn NH3 2 plus complex ion times the concentration of the OH minus ion squared. This is divided by the equilibrium concentration of NH3 to the 4th power. And this is going to equal 1.3 times 10 to the minus 7. So we can now plug in our equilibrium concentrations in order to solve for X. So in this particular case, our complex ion concentration is going to be X. The concentration of OH minus is going to be 2X. We need to square that. And the concentration of the ammonia is going to be 15 minus 4X to the 4th power. This is going to give 1.3 times 10 to the minus 7, which is our equilibrium constant for the overall reaction. Now, a lot of these problems are tricky, and they involve high-numbered exponents. So when I say to calculate the concentration of ammonia, we're going to be using approximations in every case. It doesn't matter if they don't follow the same rules as they did in chemistry 122, but for these complex ion questions, I would never give you an expression with 15 minus 4x, expect you to raise that to the 4th power, and try to solve that polynomial. Okay? It's just, the math is just too complicated, and I don't want you to deal with that math in this class. Okay? Especially when you're using a TI-30 calculator on an exam. So what we're going to do is we're going to approximate that 15 minus 4x is going to be roughly equal to 15, so we can ignore this part of the expression. That makes the math so much easier. So if we go through and calculate this, our x is going to equal 0.118 molar. And again, that's a rough approximation. Okay? So what we can say about this value for x right here is that if we assume x moles of zinc hydroxide, which is ZnOH2, dissolve, then X is the molar solubility of zinc hydroxide in 15 molar ammonia. So this is going to be drastically different than what we see in aqueous solution. So if I come back and we kind of compare, if we look at our experimental results, if we went into the lab and performed an experiment, we would show that 8.9 times 10 to the minus 7 grams of ZnOH2 will dissolve in 4 milliliters of water. Zinc hydroxide has a very, very low molar solubility in water. We're not going to get many grams to dissolve in solution. But if we compare that to the result that we just calculated, we can say that 0.0469 grams of zinc hydroxide, or ZnOH2, will dissolve in 4 milliliters of 15 molar NH3. What I want to point out here is that these two values right here are a dramatic difference. And this dramatic difference can be attributed to complex ion formation. So this shows us that we can really manipulate and we can control the solubility by using this complex ion formation and using it to our advantage. So in certain cases, when you looked at your group 1 analysis, you need to take that silver complex, and you have silver chloride, which really doesn't want to dissolve in anything. But if you add concentrated ammonia, it will form a complex ion and it will dissolve. Okay? There's other cases throughout the qualitative analysis scheme, and you're going to notice that particularly with the silver complex, we use dilute AgCl because we want to try to separate the silver from all the other ions. If we would add concentrated HCl, the complex ion would form much more readily. So that's one of the things to look at, and when you're performing the experiments, or when you're performing the steps in this particular laboratory, keep into the back of your mind which effect is happening. When is the complex ion forming, and how is that allowing us to manipulate the solubility? Another very, very common question that we'll get involving the complex ions is that a complex ion is a nice way to remove a particular ion from solution. Because in this case, zinc 2+ is completely different than the complex ion that forms, that is Zn NH3 2+. So we can effectively remove ions from solution using this complex ion formation.